The biggest star ever discovered isn't necessarily the biggest star that exists. It might not even be the biggest star we've already found. For over a decade, one star has been quietly crowned the largest known star in the universe in headline after headline. But if you actually look at how that title gets decided and how many times it's already changed hands, you find something stranger than a simple record. You find a measurement problem so difficult that astronomers still can't fully agree on where some of these stars even end. Before any of this makes sense, there's a problem hiding in the question itself. Biggest by what measure? Stars don't have a single size, the way a building or a planet does. A star can be enormous in radius but relatively light in mass. It can be extraordinarily massive but physically smaller than a star twice its radius. And it can be blindingly luminous, without being either the biggest or the heaviest. That means there isn't one competition for biggest star, there are at least three, running at the same time, with different winners. The largest known star by radius is not the same star as the most massive known star. Most explainers online quietly collapse these into one number, which is part of why the biggest star record feels so unstable. People are often comparing different contests as if they were the same race. For years, a red hypergiant called UY Scuti held the record for the largest known star by radius, roughly 1,700 times the radius of our Sunday. Picture the Sun replaced by UY Scuti, sitting in the same spot. Its outer surface would extend out past the orbit of Jupiter. Then a star called Stephenson 2-18 showed up in the data, with radius estimates suggesting it might be even larger, over 2,000 times the Sun's radius, a number so extreme that if you swapped it in for our Sun, its surface could reach close to the orbit of Saturn. Except the more scientists examined Stephenson 2-18, the shakier the claim got. It's not even fully confirmed. The star belongs to the cluster its distance estimate depends on, and if the distance is wrong, the size calculated from it is wrong too. Some later analyses put its actual radius drastically smaller than the headline number. UY Scuti's estimated size has also been revised, pulled down by newer Gaia distance measurements, in some analyses by hundreds of solar radii. So the honest answer to what's the biggest star ever discovered isn't a single name. It's a moving target between at least two candidates, with real scientific disagreement over both of their actual sizes. Part of the problem isn't the distance, it's the star itself. These aren't compact, sharply edged objects like the Sun appears to be. Red supergiants and hypergiants have extremely extended, diffuse outer atmospheres that fade gradually into surrounding gas and dust, rather than stopping at a clean boundary. Many are also shedding huge amounts of material into space, wrapped in dust shells that can be mistaken for part of the star, or that obscure where the actual surface is. That means two astronomers using different techniques, one measuring angular size directly through interferometry, another estimating it from total light output and surface temperature, can arrive at meaningfully different numbers for the same star. Neither is necessarily wrong. They're just drawing the boundary in slightly different places, on an object with no hard edge to measure in the first place. While the radius record keeps shifting between two uncertain contenders, a separate title, most massive known star, currently belongs to a star called R136A1, sitting in a dense cluster inside the Large Magellanic Cloud, a satellite galaxy of the Milky Way. R136A1 isn't unusually large in radius. It's unusually heavy, estimated at somewhere between 150 and 230 times the mass of our Sun, depending on the modeling technique used. That range matters because for decades, theoretical physics suggested stars shouldn't be able to exceed roughly 150 solar masses at all. The reason is the Eddington limit. Above a certain mass, a star's own light becomes so intense that its radiation pressure should overpower gravity's grip on its outer layers, blowing them away faster than the star could hold itself together. R136A1 appeared to blow straight through that theoretical ceiling, forcing astronomers to either revise the mass downward or accept that stars can briefly exist above what was supposed to be a hard boundary. Its mass estimate has since been revised down from even higher original claims, part of a broader pattern. Nearly every record-breaking star, studied more carefully, ends up smaller than its first headline. None of this is happening because scientists keep making mistakes. It's happening because the tools for measuring extremely distant, unusual stars keep improving, and nearly every improvement in distance measurement or direct imaging has pulled these record holders back down toward more modest, though still genuinely enormous, numbers. The Gaia Space Telescope alone has quietly rewritten the distance and therefore the calculated size of numerous record stars simply by measuring their position more precisely than ever before. Expect the leaderboard to keep shuffling as newer telescopes come online. The star holding the biggest ever discovered title right now may not hold it in 5 years and may never have actually held it correctly in the first place. There's a reason these record holders are worth watching closely, and it's not just their size, it's that stars this massive are already living on borrowed time. A star like UY Scuti or Stephenson 2-18 is classified as a red hypergiant because it has already burned through the hydrogen that powers most of a star's life, swelling outward while fusing progressively heavier elements in its core. That process has a hard stopping point. Once a massive star starts fusing iron, it's effectively out of usable fuel, since fusing iron consumes energy instead of releasing it. The outward pressure that held the star up for millions of years switches off. The core collapses in under a second, then rebounds in a shockwave violent enough to blow the outer layers into space at a meaningful fraction of light speed. That's a core collapse supernova for stars this size, not a question of if, but when. What's left behind depends on how much mass survives. For many of these giants, the crushed core settles into a neutron star, an object so dense a teaspoon of it would weigh billions of tons. For the most massive ones, there's not enough outward force left to stop the collapse at all, and it keeps going into a black hole instead. R136, a 1 raises an even stranger possibility. Stars in its extreme mass range can potentially undergo a pair-instability supernova. At sufficiently high core temperatures, gamma rays spontaneously convert into particle-antiparticle pairs, draining away the pressure supporting the core and triggering a runaway collapse, so complete it can blow the entire star apart. No neutron star, no black hole, just an expanding cloud of gas and light where the star used to be. This isn't purely theoretical, either. In late 2019, the red supergiant Betelgeuse dimmed dramatically and unexpectedly, and speculation spread that it might be about to go supernova in real time. It turned out to most likely be a dust cloud the star had ejected, not imminent collapse. But it was a reminder. Several of the largest, most unstable stars we can see are close enough that a supernova, in one during a human lifetime, isn't out of the question. It just hasn't happened yet. None of this means these stars aren't extraordinary. Even the more conservative, revised estimates for UY Scuti, Stephenson 2-18, and R136A1 describe objects almost incomprehensibly larger or heavier than our own sun, stars that, by any reasonable definition, sit at the absolute extreme edge of what physics allows a star to be. But the exact ranking, which one is the biggest, turns out to be less a settled scientific fact than a live, ongoing measurement problem, sensitive to distance estimates, atmospheric modeling, and where exactly you decide a star's edge actually is. Maybe that's the more interesting story than the record itself. Not which single star deserves the crown, but that measuring the size of something so large, so far away, and so physically strange that it barely resembles the smooth yellow disk we see every day, is still, after all this time, something astronomers are only just learning how to pin down.